Hello everybody, I'm Hamish McKinnon. I'm a market analyst at Transpower with operations division now. I'm a reasonably novice compared to Murray, so I hope Murray's level of entertainment is not the expectation going forward.
You got more of a laugh now.
Supporting me in this part of the presentation is Duncan Buchanan. Duncan's just down here in the front. He's a market systems technical specialist, so he's basically the go-to guru for the coordinators, making sure that their tools are what's right for them, basically. High-spring washers, obviously a subject near and dear to all of our hearts. Please go easy on me at the end. There was quite a lot of feedback from participants to the previous authorities consultation about high-spring washers and how we propose to treat them under real-time pricing. But largely that was positive feedback, so 12 people responded. In total, six companies agreed without elaboration that the proposed treatment was the way to go. The other 6 identified a few questions and wanted some more information, so hopefully this presentation will give you a bit of that and demonstrate the kind of work that we've been doing today. So this is the busiest slide in the set, not to fret. I often refer back to the high-spring washer presentation that's on the Transpower website. It's a very clear and accurate way of describing what is how a real physical outcome of how SPD does its solution can result in some fairly weird pricing. So this is a fairly simple sort of situation, I guess, or system where you've got a binding constraint on parallel paths between 2 generators which are widely divergent in their pricing offers. The constraint is binding, as is indicated by the dark section here, and as a result of SPD coming up with its least cost total system solution, it's looking at what would it cost to provide the next megawatt at bus B and bus C, and in doing that calculation, it's assigning the change in the total system cost at bus C, for instance, is $199, which is widely divergent from either $100 per megawatt or $1 per megawatt, which is the offered generation. Conversely, you get on the other side of the spring washer some other fairly interesting prices of minus $98, simply as a result of the same calculation, but this is the change in system cost to provide the next megawatt at bus B. So I think Murray's made a habit over the last 10 or so years of going into the real detail about interesting high-spring washers as they happen in real life on the real power system. But hopefully for today you're comfortable with the idea that this is a representative example which we might reasonably extrapolate to the full system to demonstrate that although real, SPD can come up with some pretty interesting results sometimes. So let's talk about high-spring washers as they are at the moment. So we have 2 requirements according to the definition of the code. We have a binding transmission constraint, which is demonstrated by the diagram previously, and the code defines a high spring washer price situation at the moment as the situation where resultant GXP prices are 5 times higher than the highest cleared energy offer. So I'll talk a bit more later on about how that's a reasonably arbitrary measurement, and you get a situation, or you get situations from time to time where those 2 factors which contribute to the high spring washer pricing situation aren't actually necessarily linked. So you get some situations where, especially at very low pricing, for instance, if you had, say, a cleared energy offer of 3 cents and a cleared reserve offer which might be 20 cents, the total price at a GXP might be 20, 23, 25 cents, something like that. But that's up to 20 times, a significant multiplier on the highest cleared energy offer. So there is a situation where you get that price disparity. Now, at the same time, if you have a binding constraint in the schedules, the pricing manager will inform us that there is a high spring washer pricing situation. Now, clearly those two things aren't necessarily linked. At the moment, high spring washer pricing situations happen reasonably infrequently. In the last 4 years, I think, David, your analysis demonstrated that there were fewer than 20 trading periods, and that's a very round number. I think the largest number was 15 trading periods per year. As I said, they can result in unusual prices, either high or negative. But the key point about how we treat them at the moment is that that 5 times multiplier triggers a manual intervention in the pricing schedule, which delays prices. Now, obviously, that can only happen because pricing is separate from dispatch. We wouldn't be able to apply a manual override to a pricing solution in real time because simply there isn't enough time and we need to keep dispatching the power system. So a number of participants asked how often can we expect to see similar things happen under RTP, and to be honest, there isn't a very good answer for that at the moment. But what we have done is consider the case where disregarding the arbitrary 5 times multiplier that currently exists, if we look at the way RTD solves, which is our dispatch schedule, if you look at prices that occur in the dispatch schedule that range from between $10,000 and $100,000, $100,000 being the CEIR CVP value that Murray was talking about previously, and $10,000 being sort of the limit at which we start to think about, or we would start to think about whether load needs to be managed under RTP. We get a result that says maybe 50 dispatch schedules in the last per year in the last 4 years come up with those prices in that sort of range. Now that the 10,000 is sort of the lower limit of the offer. The energy offers that exist at the moment are maxing out at around the $5,000 mark, so 10,000 would be a 2 times multiplier, for instance. So not a high spring washer under the current definition, but still a spring washer kind of pricing situation that's reasonably high. There is a caveat to that analysis that we don't actually dispatch from every RTD we produce. So if we get RTDs that have this level of pricing in certain situations, we might look to adjust the inputs to the schedule in order to verify whether those prices are correct or not. So that verification step is something that will persist into real-time pricing land and will form the basis of how we mitigate this issue. The other thing to say is that at the moment you're not seeing RTD prices, you're seeing RTP prices, which is an unfortunate similarity in the name. The 5-minute ex-post schedule is produced with slightly different inputs than the real-time dispatch schedule, and so the prices that you see in real-time aren't necessarily indicative of what the pricing schedule is coming up with. The dispatch schedule is coming up with. Well, what is an important point to realise is that even though these sorts of prices can exist in the dispatch schedule as it is at the moment, that dispatch schedule only lasts for 5 minutes. So we have a situation in RTP where we might see high prices, spring washer prices even, become more regular, but they perhaps won't persist for the same length of time. And so it'll be interesting to see whether that sort of nets off to some extent. So as I've stated before, the current treatment for what we do in final pricing for high spring washers obviously isn't suitable. We simply don't have enough time to go and take a case, analyse it, apply a correction, and put it back into dispatch. And even if we did, we wouldn't want to do that because our dispatch solution is our best estimate of system conditions at the time. It's what we need to dispatch the schedule off, dispatch generation and demand resources off. And if any constraint adjustment is going to have a consequential impact on system security. So we don't want to be applying arbitrarily a relaxation factor like we do now, simply on the basis of it's a test. So if we examine how these binding constraints come about, we're able to look at in a bit more detail why these high spring washer situations come about. So the root cause is the binding constraint. The constraints at the moment are built on the forward schedule. So the most recent PRS the most recent NRS will change to be the PRS under RTP. Will produce a set of constraints which will then be ported into the dispatch schedule. We do that for performance reasons. And when the constraint is ported into dispatch, the coordinators are able to verify that the right-hand side of the constraint is appropriate. And the way that we do this is to use a tool called RTCA. So, getting into the real nuts and bolts now, the constraints that we calculate are calculated on the basis of our offered asset ratings. So, Transpower as the grid owner provides Transpower as the system operator with these offered ratings on the basis of a 15-minute offload time. So a binding constraint, a constraint will be calculated with the right-hand side that allows the coordinators to redispatch the power system within 15 minutes if one of the branches in that constraint were to trip. So that's the fundamental of it. Dispatch. The RTD schedule and the forward schedules obviously have slightly different inputs in their load, but the schedules holds in the same way, but load is a different input slightly. And from time to time, you can have differences in the market topology input as well, although that's less frequent. And so what we have in real time is that we dispatch for a generation solution that will be applicable to the load that we expect to see in 5 minutes' time. And once we've done that, we analyse the power flows across each circuit, and RTCA, real-time contingency analysis, looks at those circuit flows and says, if one of the parallel circuits to each circuit were to trip, would we exceed the 15-minute ratings of the circuit? So in real time, what actually happens, and Duncan can back me up on this if you have any particular questions, is we have a constant process of generating the dispatch solution and then verifying that the results are accurate to what we expected to see in the dispatch solution. So we can have three possible scenarios. RTCA will see in the middle an offload time of around about 15 minutes for each branch, and that means that the constraint is correct. We've dispatched generation within the proper boundary that will satisfy that requirement. Or alternatively, we can have an offload time of less than 15 minutes, in which case the constraint limit was too high. We've dispatched outside of our physical boundary. Or we can have an offload time greater than 15 minutes, in which case our constraint was too tight. We can adjust the constraint to allow more generation to flow over those particular circuits. So when we have the situation where the offload time is less than 15 minutes, we've got a problem. If something bad were to happen, we could end up with asset damage. We need to try and rectify the situation. First thing we need to do is verify that the inputs that have resulted in the constraint right-hand side are accurate. So things that can affect that calculation are things like generators being off dispatch, either because of governor response or frequency keeping or block dispatch, for instance, or simple dispatch non-compliance, as sometimes happens. The way we model our load is on a DC power flow. So if you apply AC power flow requirements to a DC model, we have estimation factors about how much reactive power is required, and that can have an impact on branch flows. So reactive power results in more current flowing across a branch, which affects offload times. Or we can have on the load side, there's a discrepancy between the half-hour average that we've calculated and what's happening in the 5-minute period. And a simple example might be we've taken an outage with an agreement that a distribution company will control load to a certain level, and it's not happening. So we have an intervention available to us there. So that would be the enforced load agreement. But alternatively, we can see some errors in how we've estimated reactive power flows and adjust that voltage profile, or we can look at how the generators are functioning and maybe ring up a generator and say, "Oi, get back on dispatch, please." At the end of the day, if all of those things have resulted in an outcome that is that our right-hand side is wrong, then we can tighten the constraint. Alternatively, we can relax the constraint if all those inputs are found to be correct, and we've still got this adverse or this mismatch between reality and dispatch. So, as far as real-time pricing goes, our focus is going to be making sure that these constraint right-hand sides are correct. What that means for our project and the tool development that goes along with it is that we can't just have a automated resolution to a high spring washer situation as it would have come about, because we need the coordinators to make that assessment about why the right-hand side is wrong, or slightly out of whack with what we're seeing in reality. But what we can do is improve our tools to give sufficient warning, sufficient awareness to the coordinators that allows them to make those decisions rapidly. And so if a high spring washer pricing situation would present itself, either it's there for a reason, or the coordinators can take the appropriate action like I've described. I think that's me. Yeah. Has anybody got any questions? Okay.